You know that feeling when you type a prompt into ChatGPT and it just instantly spits back an answer? It feels like actual magic, right? Well, today, we're ripping back the curtain. Welcome to this explainer. We're going to uncover the hidden, incredibly high-stakes engineering reality that actually made ChatGPT possible. It's a story all about the software war rooms.
Okay, let's dive right into this because the story we usually hear is all about the AI model itself, the neural network. But look at this quote right here. ChatGPT wasn't born in a quiet lab. It was forged in war rooms. I absolutely love that. This wasn't about clean research notebooks and calm scientific breakthroughs. It was a gritty, incredibly stressful reality. We're talking about engineers wrestling with a distributed system that was so temperamental, so fragile, and honestly, so unprecedented in scale that the whole thing nearly collapsed under its own ambition.
So, let's start with Section 1, the impossible scaling problem, a problem too big.
See, the early versions of ChatGPT hit a massive, brutal wall of physics. The model was just too big, too memory-hungry to fit on any single machine or any single GPU on Earth. Literally, the physical hardware didn't exist to hold it. So the only way out was this concept called sharding. Think of it like taking this incredibly complex, massive AI brain and slicing it up into thousands of puzzle pieces. You spread those pieces across completely different processors, and then, here's the crazy part, you force them all to act as one single coherent living organism.
And to put that into perspective, we aren't talking about linking up a few dozen computers in a closet. We are talking about thousands of GPUs. The scale here is just staggering. It's mind-bending. For this to work, the data had to flow through the system like a perfectly timed river, touching every single shard on thousands of processors in the exact right order, at the precise right millisecond. No stalling, no colliding.
Which brings us to Section 2, inside the war rooms with Microsoft and OpenAI.
Now, what's really interesting about this slide is the human element. To make this unprecedented coordination actually happen, all normal operational boundaries just evaporated. You had Azure engineers flying out to San Francisco, OpenAI engineers flying to Redmond, but putting them in the same room? Total culture clash. On one side, you have Microsoft Azure, deeply rooted in enterprise-grade reliability, strict SLAs, bulletproof disaster recovery. And they're sitting right next to OpenAI engineers, whose entire philosophy was basically move fast, break things, and hey, let's just rewrite the core subsystem on a Tuesday afternoon. They had to somehow fuse these two completely opposite corporate worlds just to survive the stakes.
And that leads right into Section 3, the spectacular first crash.
So once they got somewhat aligned, the combined team tried their very first serious scaling run. Just a few hundred GPUs, testing the waters. And it failed instantly. I mean, a 15-minute implosion of absolute spectacular chaos. Processes were dying with zero explanation whatsoever. The system broke so fundamentally that one specific node reported its operating temperature was absolute zero, which, unless they secretly moved the servers to deep space, is physically impossible. Another node claimed it somehow processed 9 quintillion tokens in a single second. The optimizer diverged so violently the tracking curve looked like an earthquake seismograph.
As one of them put it, and this is just a brilliant way to describe it, the logs were a crime scene. The system wasn't just failing, it was violently hallucinating its own demise. The engineers are just staring at these dashboards in total disbelief. It was the perfect storm of mismatched assumptions. Azure's scheduler expected one thing, OpenAI's code expected another, and the whole thing just shattered.
They realized pretty fast that they couldn't just apply a quick patch. After that 15-minute meltdown, they had to do a complete top-to-bottom stack rewrite, from the basic Python scripts all the way down to the cluster scheduler, literally every layer rebuilt from scratch. But actually, scratch that, fixing it wasn't the end. That massive rewrite just marched them right into an even more terrifying issue, the dreaded 1,000 GPU scale deadlock.
Let's look at Section 4, the 72-hour deadlock.
Okay, picture this. The system is rebuilt. They push the scale over 1,000 GPUs for the very first time. Spirits are super high. For the first few minutes, it is purring. Absolutely perfect. And then, without any warning, the entire cluster just stops. Dead. Put yourself in that war room right now. Why did an entire 1,000 GPU cluster just freeze without throwing a single error? No crash, no error code, just staring at a dashboard of 1,000 paralyzed, incredibly expensive GPUs giving you zero clues.
The logs were completely useless. The traces were incomplete. The culprit ended up being this catastrophic, hidden nightmare called a distributed deadlock. Deep inside the optimizer, under incredibly specific timing conditions, a single line of code overwrote a shared memory lock. It created a massive, system-wide circular wait. Literally every single process just hung in place, waiting forever for a message from another process that was never, ever gonna arrive.
72. It took a grueling 72 hours of caffeinated engineers agonizing over traces, arguing over wild theories, and tearing through code to find that one single line. 72 hours of searching in the dark. And you know how long it took to actually fix it? 10 minutes. Unbelievable.
Moving right along to Section 5, the breakthrough, 1,000 small fixes. Let's move to this slide and see how this builds, because once that deadlock was finally cleared, the energy in the room totally shifted. The ultimate breakthrough didn't come from one single Hollywood aha moment. It was calm, resolute, relentless iteration. Thousands of tiny fixes tamed the beast. Step 1, they deployed a brand new communication protocol that massively slashed synchronization overhead. Step 2, they completely eliminated data loading bottlenecks so the system wouldn't choke on its own data stream. And Step 3, they launched a super robust checkpointing system. That way, when hardware inevitably failed, and it always does, the training could gracefully recover instead of dying completely. Piece by piece, the whole system stabilized. As you'll see on this chart, the successful training runs just kept growing. An hour, then 12 hours, then a full day, and beyond. For the very first time, the model was training without collapsing. Those chaotic crime scene logs finally went quiet, and the dashboard stayed beautifully green. The crazy thing is, the engineers didn't even cheer. They were so exhausted, they just sat there in total disbelief at the silence.
Which brings us to the final stretch. Section 6, the invisible engine of AI.
With this system holding steady at 1,000 GPUs, they pushed it, 2,000, then 5,000 processors. And that final training run, the exact one that produced the model powering the ChatGPT you use today, ran flawlessly for weeks without any drama. So the crucial point is this. When we talk about AI, we almost always talk about bigger models, right? More parameters, more data. But true AI progress, it absolutely requires monumental software engineering. We're talking orchestration layers that survive hardware failures, massive data pipelines that stream terabytes without a single hiccup, and debugging tools that span entire data centers just so humans can comprehend what the machine is even doing.
To sum it all up, the source material leaves us with this incredibly powerful thought. The model is the headline. The distributed system is the story. I love that, because without this invisible, brilliantly engineered distributed system, there is no instant response. There is no magical chatbot. There's just a giant AI model, way too large to run, sitting completely useless on a single hard drive.
Which leaves us with a pretty fascinating thing to consider. If the AI model we all marvel at is really just the user interface, what other massive, invisible distributed systems are running your world right now? Next time you use a piece of perfectly seamless technology, take a second. Remember the software war rooms, the massive scale, and that hidden infrastructure that makes all our modern magic possible. Thanks for joining me on this explainer, and I'll catch you next time.